Okay, so we've looked at analysis of a sequential circuit, and we have looked at taking a state diagram and reducing it to a minimum number of states and then synthesizing it to D flip-flops. In this video, we'll look at the entire design process. For a combinational circuit, we want to our first step of our design is fully specified with a truth table. For a sequential circuit, we need a state table for specification, or a state diagram is typically what you end up with when you first design the circuit and then go to a state table. So our design procedure, the first step is to derive that state diagram from the word description, whatever you're given, and the specifications of the desired operation. Once you can define that problem in terms of a state diagram, then you can reduce the number of states which we've shown. We can assign binary values to the states. We can obtain a binary coded state table from that, and then we can choose a type of flip-flop to be used. So far we've just used D flip-flops. We'll look at using other flip-flops as well. And then from that we can derive a simplified flip-flop input equations and output equations, and then draw our logic diagram. So that first step, deriving the state diagram, that's the most challenging part. That's really the design. It's taking that word description of how we want a circuit to behave. That word description may be incomplete or inexact, so we have to have some experience really to do it. It also assumes some knowledge of digital logic terminology, and that's part of what we're trying to learn in this class. So that interpretation requires that experience. Once we have a state diagram, synthesis can be employed, and so basically steps 2 through 7 can be implemented with logic synthesis. As long as we have an exact algorithm or formal procedures for the given steps, then it can be synthesized by a computer program, essentially. For example, a K-map minimization. We have an exact algorithm using prime implicants. We can do a maximum of 6 variables. Computers can follow the same algorithm on many more variables. Also, we have the ability, and we'll learn more about behavioral level modeling in HDL, which is powerful, and it has powerful synthesis abilities. So let's take a look at a design example where the specification given to us is just to design a circuit that detects 3 or more consecutive 1s in a string of bits coming through an input line. So we do have to figure out what are the inputs, what are the outputs, how many states do we need, but what is the real meaning? So the first step is really about asking these questions. So we asking the questions, how many inputs? It says, well, just one input line, so I guess there's just one input, and we want to detect it, so we could use one output signal to show that detection. That if we want to decide if the output signal is high or low, whether that means detection or not. So at this point we have to think about how do we proceed, and I sort of gave a clue. The proceeding is talking about asking the questions. What does 3 consecutive 1s mean? It says, should the outputs change based on input change or based on state change? We have a mealy or a more state machine. Should the input allow the output to change? How many states do we need? It's going to be synchronous, but to which clock edge? Do we need an asynchronous reset of some sort? So these lists of questions, it's going to be the answers to these questions that we're going to use to design the problem. So we can always start with our first step is a block diagram. So our block diagram, we're going to need a clock, so we can use that triangle to show the clock. This shows a rising edge. We can change it to falling edge. That if it's rising or falling edge, whoever uses this circuit will need to know that, because that'll affect the setup and hold times to the input signal X. We've used X for our input signal, Y for our output signal. We call it 3 or more 1s detector. It just says detect. So when we have a synchronous circuit, we need some timing, so it makes sense additionally at this stage to sketch a timing diagram to help figure out how are we going to get to the state diagram. So we have a clock here. The clock has both rising and falling edges. It shows 50% duty cycle. We're not designing to the timing yet, so we're not really too concerned about the duty cycle at this point, so we'll just draw some clock. And then we want to figure out what happens when X changes. What should we do with Y? So for example, let's take a look at this X. This X initially is a 0, so we have 0 ones, just trying to keep track. Then we'll show that since we're using a rising edge triggered state machine here, we'll show the inputs changing on the falling edge. So if X goes high at the falling edge, it's high. The first count is going to be on this rising edge of the clock. So there we have 1, there we have 2, there we have 3 ones. So our output should then go high. It just shows, since we're controlling it, it shows it takes a little bit of time to propagate high. And then we get another 1 on the next rising edge, so that's that's our 3 or more. And then the next edge it goes low, so since X is low, our Y needs to go low. We no longer have 3 or more. And then if we get a 1, we can start our count again, but if that goes to 0, we need to go back to 0, because the key was it said 3 or more consecutive ones, so this consecutive ones is what we have to consider. So since we didn't have consecutive ones here, we'll go back to a count of 0. And then we can start counting again, 1, 2. If we didn't use consecutive ones, this would have been 1, 2, 3, and we would have gone high. So this is our timing diagram to help us figure out how we can make a state diagram. So the next question we had was, how many states do we need? Well, it looks like we here need a state for a count of 0, a state for a count of 1, a state for a count of 2, a state for a count of 3, a state for a count of 3 or more. We could have 5, 6. But maybe this 3 and 3 or more can be the same state. In both of those states, our output Y is going to be a 1. So if we think about our count, if we have, what we have is oops, let's see if we can get this to right. We have a state where we have a count of 0, so we'll call it S0. We have a state where we have a count of 1, S1. We have a state where we have a count of 2, S2. And then we have a state where we have a count of 3. And now do we need to consider more than 3, or can we just have this be 3 or more? And we'll do a little asterisk there. So if we're in state 0, we could have, and we get an X is equal to a 0, then we still have 0. So if we're in a state, we have a count of 0 and X is equal to a 1, then we have a count of 1. But if we're in state 1 and X is equal to a 0, we need to go back. We're not holding on to that, so we need to go back to state 0. If we get a count of 1, when we have 1, then we have 2. But if we get a count of 0 when we have 2, we go back to state 0. If we get a count of 1 and we're in state, or an input of 1, I should say, if we get a 1, we'll go to state 3. And then if we have 3 and we get a count of 0, we'll still in all these states, count of 0 is going to set us back, because that sets us back, resets our counter. But if we get a 1, we can just stay here. And then what we have to consider, we don't have our outputs. These are just our inputs. Right now what we have is our state. I'll do that in blue. We have our state. We'll just say S. And what's on our transition is the input X. But Y, it needs to be the same. If we were in state of, let's say we were in state 2, and our X, here we are in state 2, if X instead of nicely, we'll go over here to this state 2, if either one, but if we're in this state 2, and if we considered here at this point X is equal to a 1, if we were in state 2 and we looked at that X equal to a 1 and we did slash 0 or or slash Y would be changing based on whether we're going here, we'd want it to be a 0, right? And here we'd want y to be a 1. But then it would change based on this x. So our y would end up going high and then low again here. And we don't want that to happen, right? Since we don't want that to happen, we want our y to transition just, cross that out, we want it to transition just based on the state. So when we're in state 0, we'll have our output y be a 0, 0, 0. And up here, only when we're in state 3 will our output be a 1. And that looks like it'll satisfy our design criteria. We'd need to additionally, eventually set up timing criteria for setup and hold times. So what we've come up with is this state machine. It's a Moore model. The output's dependent upon the state only. And the rest of the design at this point is straightforward. We could use our synthesis procedure. We could write an HDL behavioral description. And we could design it by hand. So if we were going to design by hand, which is what we've learned to do, the next step would be to make a state table. So it's easiest to go from a state diagram to this form of a state table where we have, if we're in state 0 and our output we called y, so I'll put that here, our output y, when we're in state 0, it's a 0, 0, 0, 1. If x is equal to a 0, we go to state 0 for all of these states, right? If x is equal to a 1, we go to state 1, we go to state 2, we go to state 3, and if we're in state 3 and x is equal to a 1, we just stay in state 3. So we can create that state table. From the state table, we want to get our next state equations. So it's easiest to get our next state equations if our, we need to make our binary assignments first. Making our binary assignments, if we convert to this table where state 0 is the first 2 rows, state 1 is the second 2 rows, state 2 the third 2 rows, and state 3 the fourth 2 rows, where we have x being a 0 or a 1 in each of these states. And then our state assignment for what we've assigned is that our S0 is for A, B, 0, 0, S1, 0, 1, S2, 1, 0, and S3 is the 1, 1. So if we use D flip-flops, then the flip-flop input equation can be derived directly from our next state equation. So, and that's what we've done so far. So we'll do that again. So we do that again. That's easy enough to do. We just we can make a Karnoff map, right? We can make a Karnoff map. We want to solve for the next state of A here, and we want to solve for the next state of B, and then we can also solve for Y. We can see Y is just going to be equal to AB, right? That's when we're in our present state is a 3. So we can make our Karnoff map for each of those, load our Karnoff map, and we find DA, AX or BX, DB, AX or B prime X, and Y is equal to AB. And since that's going to be that DA, that's the input to our D flip-flop, we have 2 flip-flops. We have A and 2 flip-flops, one output A, one output B, and then we can draw our logic diagram for that. So that we've practiced a few times, and it's good to practice that whole. Basically, it's the synthesis step by hand. If we were going to choose other than a D flip-flop, then we need to we need to come up with our next state equations, and then we need to come up with our flip-flop input equations. So we need a relationship between the state and the input equations for a T flip-flop or a JK flip-flop. So we need a table that lists for a given state of change the required flip-flop inputs, and that's what an excitation table is. So our excitation table is something we don't need for a D flip-flop, but we need for a JK and a T flip-flop. So our excitation table we can get from the characteristic table. So we'll do that in the next video.